Okay, let's make sure we understand what's going on here. This red curve is the graph of 3 times the quantity 2x plus 3. That's the curve along which this particle is moving. The particle could have started down here, and as it starts moving along the curve, it doesn't have to move at the same rate all the time. It could go real slow and then speed up. And the distance from the origin to that point where the particle is at any given time is the distance from here to here, which we could represent with the distance formula. But the question asks, what is the rate of change of the length of this blue segment at the exact point in time when the x-coordinate is 3? By the way, I think that this probably should say through the point 3, 9, not the line 3x, 9. Anyway, so a function for the distance between the origin and where the particle is at any given point in time would be the distance formula. Distance is the change in x squared plus the change in y squared. And the y coordinate of the point or the particle is 3 times the square root of 2 times whatever the x coordinate is plus 3. So if I want to simplify this, the formula for the distance is the square root of x squared plus, well, if I square this quantity, get 9 times the quantity 2x plus 3. And if I distribute that, and I'm going to write it like this, I get plus 18x plus 27. This is a related rates problem. As the x-coordinate changes its speed, so does the distance between the position where the particle is and the origin. So we want to take the derivative of both sides with respect to t. And here, oh, this is to the 1/2 power, sorry. First, I'll apply the power rule. 1/2 times x squared plus 18x plus 27 to the minus 1/2 times the derivative of the inside, which will be 2x plus 18 times the derivative of x with respect to t. So power rule followed by the chain rule followed by the chain rule. And we know we want to find the derivative of capital D with respect to t, given that when x is 3, dx dt is also 3 units per second. So it's a matter of substituting these values, into this formula and evaluating for dd dt. So dd dt, I'll just get us started here and let you finish it up, equals, for dx dt, I'm going to substitute 3 units per second. In the numerator, I'll have 2x plus 18, but I'm putting in 3 for x, so that's 6 plus 18 is 24. In the denominator, I have this 2 from the 1/2 fraction, and I've got the square root of, well, let's see, when x is 3, 9 plus 54 plus 27, I think that's a 90. So it's a matter of simplifying this. And I believe if you put it in simplest radical form and cancel out and all that stuff, you get something like 6 radical 10 over 5. And that will be in units per second also, the distance between the origin and the particle.